Welcome to Lecture 3.2, Computing Fourier Series and Exploiting Symmetry. In the last lecture, we learned what a Fourier series was. It's a way to write a periodic function f of x as a potentially infinite sum of sine and cosine waves. And I gave you explicit formulas for computing the coefficients, namely a0, an, and bn. Those all involved integrals which were derived from inner products. Fortunately, we don't always have to compute those integrals, and when we do, sometimes we can simplify them. So there are many, or at least several, shortcuts for computing Fourier series in many cases. To begin, we need two simple definitions. A real-valued function f is even if f of x equals f of negative x for all inputs x, and odd if f of x equals negative f of negative x for all inputs x. If I draw a picture of this, it should be clear what this means. So let's sketch a function. Say this is f of x, and let's say this is x naught right here. Then a function is even if we take negative x naught, and, well, f of x naught is up here, and that has to be equal to f of negative x naught. So this just means that the function is symmetric about the y-axis. That's all it means to be even, graphically, is that f of x is symmetric about the y-axis. So examples of even functions are like x squared, or x to the fourth, or x to the 2k, where, well, that forces the exponent to be even. Other examples of even functions involve cosine, or anything like cosine of x, cosine of 2x, or cosine of nx. Now a function is odd. This is a little bit more complicated, but not too bad. So let's sketch the same piece up here. Suppose this is f of x, and say this is x naught. And so this height is f of x naught. Well, then this says that f of x equals negative f of negative x. So if we take negative x naught over here, I don't know if I've drawn this nicely, but I guess I should maybe draw it up here. Then that's just saying that this point here should be, let me extend this axis. So this is f of negative x naught, which is negative f of x naught. So that's the relation of what it means to be odd. And that just means that this graph is if I take this piece and I reflect it across the y-axis and then the x-axis, that's when I get symmetry. So sometimes we say it's symmetric about the origin, because if I draw a straight line, so if I take f of x naught and I draw and I connect that with f of negative x naught, then it should go right through the origin. So we say that it is symmetric about the origin. And that holds for every point on the graph. Examples of odd functions include things like x cubed, or x to the fifth, or x to the 2k plus 1, or things like sine of x. So any sine of x, or sine of 2x, or sine of can't decide between n and k, say sine of nx, that is an odd function. To summarize, all of the following are examples of even functions. X to the n, where n is even, cosine of nx, or any function that's symmetric about the y-axis. The following are examples of odd functions. X to the n, where n is odd, sine of nx, or any function that's symmetric about the origin. And of course a whole bunch of functions are neither. Things like x squared plus x cubed, e to the I nx, which is cosine nx plus I sine of nx, are functions that have neither type of symmetry. And even more than that, the reason why functions like cosine of nx are even are because their Taylor series are comprised of only even powers of x. So cosine of nx, if you recall, is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus minus etc. And sine of nx contains only odd powers of x. Now, the even functions form a vector space. If I take things like x squared minus 3x to the sixth plus cosine of 2x, I still get an even function. These are closed under addition and also under scalar multiplication. 0 is an even function. 0 is also an odd function. It satisfies both of these easy requirements. And the odd functions are vector spaces as well. If I take x cubed plus 1/2 x to the 11th, or I subtract 1/3 sine of 4x, this is an even function. They're closed under addition and under scalar multiplication. Okay, so why do we care about this? Well, a nice property about even functions, we will apply this to Fourier series in the next slide, is that if f is even and we want to integrate it from negative L to L, then all we have to do is integrate it from 0 to L and multiply by 2. I should be able to convince you of this with two simple pictures. So if f is even, then it looks something like this. And if I want to integrate it from negative L to L, then that's just the area under the curve. And by symmetry, it should be clear that this area under the curve is just twice the area from 0 to L, just by symmetry. And that's why we have to integrate from 0 to L and multiply by 2. Now if f is odd, you likely see where this is going, and I have an odd function, something like this, and I want to integrate from negative L to L. Well then, the integral is signed area, so these areas are the same, but they cancel each other out. So this area, same as that area, and that's why I get 0. So now I haven't directly applied this to Fourier series, but I'll do that on the next slide. Let's suppose we have a function f of x that's written in a Fourier series. So a0 over 2 plus an infinite sum of sines and cosines. Now we have a big shortcut and a small shortcut regarding symmetry. First of all, if f is an even function, then I claim every bn is equal to 0. So if f has this even symmetry, if it's like symmetric about the y-axis, something like this, and we want to write this in terms of sines and cosines, then I claim that it is only going to contain cosine waves because they have the same type of symmetry as the same type of even symmetry as f, and they will not contain any sine waves because sine waves have odd symmetry. And so in other words, there cannot be any pieces, any components, or any sine terms in an even function. Even functions are entirely contained of, are entirely composed of cosine waves and possibly a vertical shift. So hopefully this picture convinces you of that, or at least gives you evidence that you believe it. But let me show you the algebraic reason. So Bn, by definition, is the inner product of f with sine of n pi x over L, which, given our definition of inner product, is 1 over L times the integral from negative L to L of f of x times sine of n pi x over L. Now, if we take an even function and multiply it by an odd function, we get an odd function. I haven't proven that, but just think about something like x to the 4th times x cubed. Even functions are comprised of even exponents, or even powers of x, and odd functions of odd powers of x. And if I multiply those together, the exponents add, and if I take an even plus an odd, I get an odd. So in other words, Bn, in this case, is an integral from negative L to L of an odd function divided by L. And so if we integrate an odd function from negative L to L, as we just saw on the previous slide, we get 0. Similarly, if f is an odd function, then I claim that all of these an's have to be 0. And that should make sense pictorially as well. So if we have an odd function, so here's an example of an odd function. Here's a square wave, something like like this. If I want to write that using sines and cosines, well, then this just says that this function can be written using these sine waves. Oops, that should be up a little bit. But it cannot contain any cosine waves. It cannot contain anything like this. The sine waves have the same type of symmetry as the odd functions, but the cosine waves do not. So it can contain these and cannot contain those. Hopefully that is also pictorially clear. Here's the algebraic reason. an is by definition the inner product of f and the cosine term, which is 1 over L times the integral from negative L to L of f times cosine. And if f is an odd function, then f times cosine is an odd times an even, which is an odd. And once again, we're integrating an odd function from negative L to L. We get 0. So I call this a big shortcut because if we know that f is even or f is odd, then we don't even have to compute one of these integrals. We know that either an or bn is going to be 0. Here's a smaller shortcut. This isn't necessary, but it sometimes makes things easier. So if f is even, then we know that the bn's are equal to 0, but I claim we have a simpler formula for the an's. So once again, an is the inner product of f with the cosine term, which is 1 over L times the integral from negative L to L of f times the cosine term. And now we have an even function times an even function, which is even. So if we integrate from negative L to L, an even function, that's the same as integrating from 0 to L and multiplying by 2. Similarly, if f is odd, then bn, by definition, is the inner product of f and a sine term, which is 1 over L times the integral from negative L to L of f times sine of n pi x over L. And now we have an odd function f times an odd function sine, and odd times odd is even. So now, as before, we're integrating an even function from negative L to L, which is that integral times 2, but from 0 to L. So here's the corresponding formula when f is odd. Let's do a few examples. Here's the first one. Consider the square wave of period 2 defined as follows. So I'm going to sketch this. So from negative 1 to 1, here's 2, here's 3, here's negative 2. So the square wave is 1 here and it's negative 1 there. So that's how it 1 from 0 to 1 and negative 1 from negative 1 to 0. And I'm saying it has period 2, so I'm forcing it to be periodic. So it looks like this. Now sometimes I draw dashed lines, or if I really get lazy, I just don't even dash them to be vertical. Now notice I have not actually specified what the function is at these breakpoints, at 0, 1, and 2. Is it equal to 1, or is it equal to negative 1, or something else? So it turns out it's not going to matter. I can make it whatever I want to. So I can put less than or equal to signs here. It's not going to change the actual an's or bn's because those integrals do not depend on whether or not this is a less than or equal to. But that said, we're going to come back to this because our answer is going to tell us is going to have some information about this. So we will revisit this shortly. Right now, this function is odd, and so we know that all of the an's are 0. So a naught is 0, and an is 0. And we also know that bn, I'm going to write down the definition. So bn is 1 over L, which is 1 over 1, times the integral from negative L, negative 1 to 1, of f of x sine of n pi x over L, which is 1, dx. Now, f of x is not continuous. So if we want to actually write out this integral, we need to do it into two pieces. We need to break up the part from -1 to 0. Let's put a 0 here. And then we need to integrate it from 0 to 1. So we would have to write this as -1 to 0. Now, what is f of x from -1 to 0? That's just -1. So that's -1 times sine of n pi x dx plus the integral from 0 to 1. Now this piece here, f of x is equal to +1. So we have to write +1 sine of n pi x dx. And now we can compute these two integrals separately. Or, here's a better way to do this. Oops, let me get my pen back. I'm going to use my small shortcut and say, hey, this function is odd. If I want to integrate it from -1 to 1, all I need to do is integrate it from 0 to 1 and double it. So now if I integrate from 0 to 1, the function is continuous in 0 to 1. I don't need to do it into two cases. So I just write 1 times sine of n pi x dx. So this is why the shortcut's a little bit nice, because it saves us doing an integral. Turns out these integrals are going to be the same by symmetry, but it's still arguably nicer this way. Okay, so let's do this integral. This is 2 over n pi times cosine of n pi x. And then I think I need a negative sign here from 0 to 1. And so now I'm going to, let's see, I'm going to do two things at once. Instead of doing cosine, plugging in 1 and subtracting 0, and a negative sign here, I'm going to plug in 0 and then subtract plugging in 1. So I'm going to write this as 2 over n pi times cosine of 0 minus cosine of n pi times 1. Okay, now cosine of 0 is equal to 1, right? And cosine of n pi, what is that equal to? Well, let's look at the unit circle to remind ourselves. So the unit circle, if I take, this is theta, then the x value is cosine of theta. So this point on the unit circle here, this is 1, and that's equal to cosine of 0 radians, or cosine of 2 pi radians. If I go around twice, that's cosine of 2 pi, or just cosine of n pi, where n is even. And -1 is equal to, this is -1, which is cosine of pi, if I go around pi radians, or 3 pi radians, or cosine of 3 pi, or it's cosine of n pi if n is odd. So it turns out that cosine of n pi is equal to +1 if n is even, and -1 if n is odd. And the quickest way to write that is -1 to the n. So that's a shortcut. Every time you see cosine of n pi and n is an integer, change that to -1 to the n right away. It's going to make your life easier. So now I'm going to write this. This is 2 over n pi times 1 minus -1 to the n. And I will say that sometimes it helps to see this for what it is if n is even, then we get 1 minus 1 and we get 0. And if n is odd, then we get 1 minus -1, which is 2. So I'm also going to write this as 0 if n is even, and 4 over n pi if n is odd. So this is what Bn is equal to. Two different ways to write it. This is maybe more intuitive as to what it is, and this way is nicer in a math equation. So f of x right here, I'm going to write this as, well, let's think about what this means. So as a Fourier series, f of x is an infinite sum of sines and cosines. Now, all of the cosine terms are 0, so I'm only going to write the sine terms. So it's 2 over n pi times 1 minus negative 1 to the n times sine of n pi x. That's what f of x is. So this is the Fourier series of this function. Now let me write it one more way. So f of x, I'm going to just plug in the first 7 terms. So sometimes this compact notation is nice, but it's not as apparent as if I write it out as a long infinite sum. So let's do that. So I'm going to write out the first n equals 1, 2, 3, etc. So remember, all of the even terms are going to be 0. So I'm only going to write down the odd terms. So f of x for each odd term is 4 over n pi. So f of x is 4 over 1 times pi times sine of n, oh, not n, sine of 1 times pi x plus 4 over 3 pi times sine of 3 pi x plus 4 over 5 pi times sine of 5 pi x plus 4 over 7 pi times sine of 7 pi x plus dot dot dot. So this is another way to write this same function up here. Actually, let me redo that. I thought I was just going to take away the box, but it took away everything. Okay, so I think this is a little more intuitive to see. It's an infinite sum. All of this is a little more compact. Finally, let's go back to this graph, which unfortunately overlaps a little bit with the box that I've done. So here's our function. Now what happens if I take this thing that we got, this is defined everywhere, and I plug in 0? So let's do that. So what's f of 0? So f of 0 is, well, each of these terms is sine of 0 is 0. So if you plug in 0 into this function, you're going to get 0. And same with plugging in 1 or 2 or 3. Sine of pi x is always, n pi x is always equal to 0. So this function here, we don't have any control over it. At the discontinuity points, it is equal to 0. So that's why I said I wasn't too concerned about what I declared or defined f to be at these discontinuities, because in the end I don't have any choice. When you compute the Fourier series, if you have any discontinuities, it will always be the case that that function converges to whatever the average value of those 2 breakpoints are. Here's our second example. Consider the sawtooth wave defined by f of x equaling x from negative L to L and extended to be periodic. So let's draw a picture of this. So now we are defining, let's say this is from negative L to positive L. So here's the function x, and now we're saying extend this to be periodic, which means we are going to make it like this. So this is now 3L and etc. So this is called a sawtooth wave in engineering, and we want to find the Fourier series of this. So as before, this is an odd function. So all of the ANs, A0 and AN, are going to be equal to 0. Okay, so let's compute the BNs. So the BN, well, right away I'm going to say, since this is an odd function, I'm going to integrate from 0 to L and double that. Although it doesn't really matter here. It's not a big shortcut because there's no discontinuity in here, so it's not a big advantage. But it's a good habit to get into. So I'm going to integrate, take 2 over L, integral from 0 to L of x times sine of n pi x over L dx. So now I need to do this by parts. I need to let let u be equal to x, say u, and du be dx, and dv has to be this sine term. Oops, I meant to use my laser pointer. That's dv. So dv is sine of n pi x over L. And then v is cosine. Oops, let's be careful here. So we're going to divide. So we're going to say L over n pi times cosine of n pi x over L. And do I need a negative sign here? Yes, I do. Okay, so now this integral, let's write it as Bn is 2 over L. Now it's u times v, so that's this times, so u times v is x, the negative xl over n pi times cosine of n pi x over L. That's uv minus v du. So this is v du, so that's minus, so L over n pi times cosine of n pi x over L. And this is, again, this is from 0 to L, and we have to evaluate this from 0 to L as well. Okay, so let's do this. So what happens? It's not clear how this is going to simplify. So this is 2 over L, and now let's plug in. So once again, I'm going to, one quick thing. I said minus v du, and there's a negative sign here, and there's a negative sign minus v du, so I need to make that positive. Okay, so we got to be careful with this. It's easy to mess up a sign, S-I-G-N. So this negative sign, I'm going to make it positive, and then I'm going to switch the 0 and L. So I'm going to plug in 0 first. If I plug in 0 first, I get 0 because 0 goes into x. So I'm going to get 0 minus what I get when I plug L in. So if I do that, I get L squared over, make sure I'm doing this right, yeah, L squared over n pi times cosine of n pi x over L, which is cosine of n pi. So this is cosine of n pi. Now remember, unit circle, cosine of n pi, that's the points here. So cosine of n pi equals negative 1 to the n. And I should say, I think this will be useful in this problem, sine of n pi is equal to 0, because sine of n pi is just the y value at these points, and that's equal to 0 because we're on the x-axis. So right away, this we can make negative 1 to the n. So now what's this integral equal to? Well, if we integrate this, we get plus, I'm going to pull out the constant, L squared over n squared pi squared, because I'm dividing by n pi over L again, times sine of n pi x over L, and I integrate that from 0 to L. Now right away we see if we plug in L, we get sine of n pi L over L, or sine of n pi, we get 0. And if we plug in 0, we get 0 as well. So this whole term is just 0. So this simplifies as, let's see, how does it simplify? We have an L squared here and an L on the bottom. So this is equal to negative 2L over n pi times negative 1 to the n. And this, let's see what this is. This is, well, it's just that, yeah. This is either plus or minus 1. Well, I guess I can write it. If I want to, I could say this is equal to 2L over n pi if, I've got to be careful, it's a negative here. So if I want to, I could, let's make that positive and let's put an n plus 1 here. So now this is going to be odd, or this is going to be negative precisely when n is even. That's when n plus 1 is odd. So when n is even, and it's going to be negative 2L over n pi when n is odd. So let's do what we did before. Let's write this function with the first few terms of this. So f of x, I'll write it two different ways. It's the infinite sum, n equals 1 to infinity, of this guy, of 2L over n pi times negative 1 to the n plus 1 times sine of n pi x over L. And if I want to write this out for a few terms, let's do that. So when n equals 1, that is, let's see, when n equals 1, again, it's an odd, so this is going to be, oh, hold on, did I say it backwards? When n is even, this becomes an odd number and this becomes negative. So I think, yeah, I had it backwards. So let me put a plus sign there and a negative sign there. So it starts at n equals 1, so that's going to be positive. So this is going to be 2L over pi times sine of pi x over L minus 2L over 3 pi sine, sorry, 2I over 2 pi, I forgot that I'm over sine of 2 pi x over L plus 2L over 3 pi times sine of 3 pi x over L minus 4L, not minus 4L, got carried away there, minus, everything's 2L over 4 pi times sine of 4 pi x over L. It's easier if L is equal to pi. These things cancel a lot better. Plus or minus, so forth. So we get this infinite sum. Now we have even and odd terms. And yeah, so this sum is, if we actually plug in our breakpoints, if I plug in L here, I'm going to get, so let's do that. Let's plug in L, and now we get sine of n pi x over L. That's 0, so we get 0, not surprisingly, as I won't prove it to you, but I'll tell you that that's what always is going to happen. So this is the Fourier series of this sawtooth wave. Two different ways to see it. There's the compact notation like this, or you can write it out explicitly as an infinite sum like that. And here is the picture. Example 3. Consider the function defined f of x equals x squared on negative 1 to 1 and extended to be periodic. So let's draw a picture of this. So now we have this looks like a parabola, and it just repeats like that. So this is 1, this is negative 1, and this is 1. Notice I didn't have to worry about defining this on an open or on the boundary, because this function is actually continuous. So I didn't have to put the open integral or interval here or worry about these breakpoints. Okay, so this is an even function, first of all. So this is even. So we say right away that all the bn's have to be equal to 0. And now the an's, remember we have formula a naught. Let me do an first. So an is 1 over L, from negative L to L, f of x times sine, or not sine, sorry about that, cosine of n pi x over L dx. And then a naught, the formula is the same thing. It's just take cosine of 0, which is 1. So you get the integral from negative L to L of f of x dx. Now, you have to compute these things separately, because the technique of integration for, say, an x squared times cosine is much different than just x. What you can't do is just integrate x squared times cosine of n pi x over L and then just plug in n equals 0, you don't get the same integral as just integrating x squared. So even though the formulas are the same, or this is a special case of that formula, you need to compute the integrals separately. So here L is equal to 1, because we're going from -1 to 1. So A naught is, well, I'm going to do the shortcut right away. I don't need to because it's continuous here, but I'm going to take 2 times the integral from 0 to L of x squared dx, and I get 2x cubed over 3 from 0 to, I said L, this is 1, and so this is 2/3. So A naught is 2/3. And AN, well, this is going to be messy. This is 2 times the integral from 0 to 1, or doubling it again, going from 0 to 1, of x squared times cosine of n pi x over L, L is 1, dx. So this is where I do not want you to compute this integral by hand. This is that's something you should do in Calc 2. By now, just plug it into a computer. Now, don't plug the definite integral in for several reasons. First of all, your computer, Wolfram Alpha or MATLAB or whatever, is not going to know that n is an integer. So just plug in the indefinite integral. And so I did this right now in Wolfram Alpha, and I'm looking at it on my computer, and what I get is I get that this indefinite integral is pi squared n squared x squared minus 2 times sine of pi, I like to write n pi x, but Wolfram Alpha likes to write pi nx, plus 2 pi n x cosine of pi nx all over pi cubed n cubed. And now the Wolfram Alpha says plus a constant, but we're integrating from 0 to 1, so let's put 0 here and 1 here. Okay, so before we plug these in, let's do some pre-processing or some thinking. So look at this first term. This is sine of pi nx. Now if we plug in 1 into that, we get sine of n pi. Remember that sine of n pi equals 0, and cosine of n pi equals -1 to the n. Always remember those. So when we plug 1 into this, I don't care about this pi squared n squared x squared term. When I plug 1 into the sine term, that goes away. And when I plug 0 into the sine term, sine of 0 is 0 as well. So we can just ignore that term. That's going to go to 0. Now, the second term, well, when I plug 0 into the second term, I'm plugging 0 in for x, that goes away as well. So the only non-zero thing I'm going to get is when I plug 1 into this term up here. So if we do that, we get 2, that's already outside, times 2 pi n cosine of n pi, I still like writing n first, divided by pi squared, or pi cubed, n cubed. And if we simplify this, we get 4. What do we get? We get 4. We have an, let's see, let's do the bottom first. 4 times, because the pi's are going to cancel, so we get a pi squared on the bottom and we get an n squared on the bottom. So 4 over pi squared n squared times -1 to the n. So there it is. So our Fourier series, f of x, is a naught over 2. Now a naught is 2 over 3. So a naught over 2 is going to be 2 over 6. So that's 1/3. So it's 1/3 plus the infinite sum from n equals 1 to infinity of 4 over pi squared n squared times negative 1 to the n times cosine of n pi x. So there's my Fourier series. If you want, you can write this as 1/3 plus, let's see, so let's be careful here. So plus, actually, I'm going to do minus first because when n equals 1, this is negative. So minus 4 over pi squared cosine of pi x plus 4 over pi squared 2 squared, so that's 4 pi squared cosine of 2 pi x. Let's do 2 more. Minus 4 over 9 pi squared cosine of 3 pi x plus 4 over 16 pi squared cosine of 4 pi x plus minus, etc. So 2 different ways to write this. Now this is the first non-odd function that we've done, and notice that with a non-odd function we get an a-naught term that is not necessarily 0. So we get this non-zero term here. And I want you to think about what that means. I claim that this term 1/3 is actually the average value of this function, and here's how to think of it. So ignore this term. Look at just these cosine terms. Add these up together, and however you will, the average value of these cosine waves, whether you have one of them or a sum of 10 of them or infinitely many of them, the average value, that's the average height, is going to be 0. Because cosine waves are symmetric. I mean, they spend just as much time above it as below the axis. This function does not have an average value of 0. It has an average value of 1/3, calculus exercise. So the only way we can get that average value of 1/3 is by this a-naught over 2. That's the vertical shift that shifts everything up by the average value. So hopefully that convinces you that this a-naught over 2 term is the average value of f. This is important enough to state as a proposition. So for any Fourier series, the average value of f of x is the constant term a-naught over 2. And again, the reason why this is the case is because if you take the sines and cosines, no matter how you want to add sine and cosine waves together, so here's maybe a cosine wave, maybe here's a sine wave, however you do it, doesn't matter the frequency or the amplitude, the average value of each of these, and therefore the sum is going to be 0. So the only way you can actually get the sum to have an average, the function to have an average value of something non-zero, is to shift it up by a constant a-naught over 2. This reminds me of a fun quiz I used to give. Well, fun for me, depending on who you are, I guess. Let me sort of sketch what it used to be like. So I used to draw a function like this by hand, and then I would say, so it was something like this. I say, suppose this is a function and we compute its Fourier series. This is before I ever told anyone the fact about this. I wanted to see if they could figure it out for themselves. And suppose this is 10. I would say compute a-naught over 2. So of course a lot of students would just guess that, well, this is the constant term, maybe you plug in 0 and maybe it's 10. Or some people would guess 20 or guess 5 because of this divided by 2. But if you look at this function, the average value of this function is really small. It's down here. So I would say that the a-naught over 2 is approximately equal to 1. So students would only get this right if they would think about it and intuitively figure out what the average value represented, and then it's clear. The a-naught over 2 is going to be approximately 1, not 10. I'm going to conclude with an exercise just to help us better understand Fourier series. So consider a Fourier series, a-naught over 2 plus the infinite sum of sines and cosines. I'm going to just let L be equal to pi, so we have nx and instead of n pi x over L here. So let's draw it. Let's suppose this function looks, I don't know, something like this. And I say, what do I get if so I'm going to draw 3 things. consider this function f of x, but reflect it across the y-axis. So if I do that, this first one, if I reflect it across the y-axis, it looks like this. All right? Sorry about my artistic renditions. The second one is, suppose I reflect it across the x-axis. So that is going to be, oh boy, so we're starting with this function and reflecting it across the x-axis. Well, I should have planned ahead with this one. Oh well. Hopefully this isn't too bad. So that's what I get if I reflect across the x-axis. And now what if I reflect across the origin? So if I do that, now it looks like this. So if we know suppose we know the Fourier series of this function here. What is the Fourier series of these three functions, these reflections of them? I'm going to answer that pretty quickly, or very straightforwardly. This is a good exercise because it's a test to see whether you can understand this. So what is this function, first of all, if it reflected across the y-axis? I claim that this function is f of negative x. See that? F of negative x takes this and it reflects it across the y-axis. What is the function that's reflected across the x-axis? Now be careful here. A middle schooler could tell you any function reflected across the y-axis is just this negative. This is negative f of x. And finally, the function reflected across the origin, this is negative f of negative x. So the function is odd if this function is equal to that. This one clearly is not. So now, what's the Fourier series of these new functions? Well, let's look at the original Fourier series and notice that if I take cosine of negative nx, that's just equal to cosine of nx. Negative signs get absorbed in cosines, but if I take sine of negative nx, the negative sign pulls out. That's negative sine of nx. If you want to check that, just look at the unit circle and compare theta. Compare the cosine of theta to the cosine of negative theta. They have the same x values, but they have opposite y values. The cosine is the x value, the sine is the y value. And that holds for any theta, including nx. So the Fourier series of f of negative x is just what you get when you plug in negative x in for x in here. So f of negative x equals a naught over 2 plus the infinite sum. I'm not going to write 1 to infinity. What happens? The negative sign gets absorbed in cosine and it pulls out of the sine. So I get an cosine of nx minus bn sine of nx. Similarly, negative f of x just multiplies this whole thing by negative 1. This is negative a naught over 2 plus negative an cosine of nx minus bn sine of nx. Don't be scared by the infinite sum. You're just multiplying this thing by negative 1. And finally, this one, well, you're taking the negative of this first guy. So this is equal to negative a naught over 2 plus negative an cosine of nx plus bn sine of nx. And if you think about it, this makes sense because when you are, so here's the picture of the cosine versus the sine. If I look at the cosine wave, cosine of negative x equals cosine of x. If I reflect this across the y-axis, I get the same thing. But if I take the sine wave and I reflect this across the y-axis, then I get sine of negative x equals negative sine of x. So this first one, the bn's flip SIGNs become negative and the ANs are preserved. For this last one, the ANs become negative and the BNs are preserved. And for negative f of x, the second one, everything switches sign. Okay, so that was just an exercise just to test your versatility and your knowledge of these things. And I think that is a good place to stop.